Welcome to this explainer. Today, we're diving straight into the exact mechanics powering a 2026 large language model. If you're gearing up for a machine learning or data science interview, you know this landscape moves unbelievably fast. So, we're going to unpack the entire stack, the architecture, the training pipelines, and the latest inference techniques. Let's get you ready to absolutely crush that next technical interview. I mean, ask yourself, how does a modern model actually remember a million-word document? How does it reason through a massive multi-file code base? Or act as an autonomous agent that just goes out and invokes external APIs? We aren't just talking about your basic chatbots anymore. We're talking about highly specialized omnimodal reasoning engines.
Okay, let's map out our curriculum. First up, the paradigm shift, then the core engine, followed by the assembly line. After that, we'll look at the output layer, and finally, wrap up with some real-world applications.
So, part 1, the paradigm shift from narrow to general AI.
The sheer scale of this architectural leap is honestly pretty staggering. Back in the day, traditional models relied on things like n-grams and hidden Markov models. They were super narrow, locked into specific domains, and ran totally fine on standard CPUs because, well, they just guessed words based on a tiny fixed window of past text. But 2026 large language models? Oh, totally different ballgame. They've universally standardized on causal decoder-only structures. We're talking massive parameter counts deployed across hardcore GPU clusters, acting as general-purpose reasoners that can handle zero-shot logic across completely unrelated fields.
Just to put that into perspective, take GPT-4 from back in 2020. It was a dense model with 175 billion parameters. That meant every single parameter fired for every single word, which really bottlenecked its efficiency, plus it had a tiny context window. Now compare that to the GPT-4 lineage today. We've shifted over to a sparse mixture of experts architecture. Basically, the model routes tasks to specific expert subnetworks, saving a massive amount of compute. It's natively omnimodal, effortlessly processes 128,000 tokens, and uses inference time scaling for really complex System 2 chain-of-thought reasoning. Moving right along to part 2, the core engine and the mechanisms of scale.
All right, the absolutely crucial point here is the scaled dot product attention formula. If you want to ace your interview, you've got to know this one cold. This single equation completely replaced the slow step-by-step processing of old recurrent neural networks. It literally allows the model to look at an entire massive context window all at once. By calculating this formula, which, by the way, is usually optimized in 2026 by hardware-aware algorithms like FlashAttention 3, the model dynamically spotlights exactly which previous words are most relevant to the word it is generating right that very second.
To really wrap our heads around this, let's break that formula down into 3 simple vectors: query, key, and value. Think of it kind of like a giant filing system. The query is what the current word is actively searching for, say an adjective looking for its noun. The key is the label on all the other words in the sentence telling us what information they hold. And when a query and a key align perfectly, boom, the model extracts the value, which is the actual semantic content. This parallelable matching system is literally the beating heart of the transformer.
But, of course, there's a catch. As context windows explode well past 1 million tokens, standard attention hits a massive wall. Standard self-attention has an O of n squared complexity, meaning if you double the context length, your compute requirement quadruples. To survive in 2026, the industry is increasingly hybridizing with, or completely shifting to, state space models like Mamba 2. These give us linear O of n scaling, letting us process near infinite context windows without completely melting our GPU clusters.
So wait, if attention processes everything all at once, how does the model actually know word order? The dog bit the man, and the man bit the dog use the exact same words, right? Well, the answer in 2026 is ROPE, or rotary positional embeddings. Instead of just slapping on static positional tags like the older models did, ROPE injects relative positional data by physically rotating the query and key vectors in a complex mathematical space. It's a total game changer because it allows models to smoothly extrapolate to sequence lengths way beyond what they were originally trained on.
All right, part 3, the assembly line, looking at modern training pipelines. This 4-step blueprint right here is pretty much everything you need to know about the modern training pipeline. First up, self-supervised pre-training. That's where the model ingests petabytes of data, just learning to predict the next token. Then comes supervised fine-tuning, where human-curated instruction sets teach it to format responses properly. Step 3 is alignment, which ensures the model is safe and helpful. And finally, we have parameter-efficient fine-tuning, like LoRa. That's where we can specialize these massive models for specific domains, like medicine or law, by updating just a tiny, tiny fraction of the overall weights. And definitely jot this down for your interview. Direct Preference Optimization, or DPO, is now the industry standard, completely taking over from the older RLHF method. Historically, aligning a model meant you had to train a separate reward model, which was complex and incredibly expensive compute-wise. DPO just bypasses all of that. It directly optimizes the language model to favor high-quality outputs based on simple preference pairs. It radically improves alignment stability and drastically lowers your computational overhead.
Let's jump to part 4, the output layer, and how these models actually generate text. When it comes to actually generating the text, beam search is a foundational decoding method you absolutely have to know. Instead of just greedily picking the most likely next word, it explores a graph and maintains a set number of active sequences, or beams, to find a higher global probability for the whole sentence. Now, it's fantastic for short, precise tasks like translation, but for long-form generation, it can kind of get stuck in repetitive loops, which is a frustrating little phenomenon known as semantic collapse. And because generating one token at a time is painfully slow, 2026 relies heavily on speculative decoding to turbocharge the process. Imagine you have a massive, sluggish LLM. Speculative decoding introduces a tiny, lightning-fast draft model that races ahead and guesses the next several tokens. Then, the massive target model validates all those guesses in a single parallel sweep. If the draft model was right, boom! You just generated multiple tokens for the time cost of one, easily doubling or tripling your generation speed without sacrificing a single drop of quality.
Now, for that human-like variance in 2026, we've moved way beyond basic temperature adjustments to something called min-p sampling. Instead of just arbitrarily cutting off the vocabulary, min-p dynamically filters choices based on a percentage of the top token's probability. So, if the model is super confident in one word, it ruthlessly prunes the other options. But if it's a bit uncertain, it keeps a wider vocabulary open. It brilliantly balances deterministic accuracy with true human-like creativity.
Modern conversational AI isn't just chatting anymore, it's autonomously executing tasks. A 2026 chatbot utilizes function calling, meaning it outputs structured JSON to autonomously invoke external APIs. It manages long-term memory through vector databases, using cosine similarity to recall past conversations flawlessly. It leverages chain-of-thought reasoning to create a little internal scratchpad before it speaks. And it uses strict pedantic validation to ensure the data it extracts is perfectly type-safe for back-end systems. It's basically a full-stack developer in a box.
Finally, part 5, applications and how we're using this in the real world.
The real-world applications are just staggering. In molecular engineering, models like AlphaFold 3 use transformer architectures to map molecular strings and predict 3D protein structures, which is massively accelerating drug discovery. In law, agents like Harvey AI ingest massive 2 million token context windows to synthesize case law and redline contracts. Over in quantitative finance, FinGPT processes alternative data for algorithmic alpha generation. And in education, systems like Conmigo act as Socratic tutors. They don't just give you the answer, they actively guide you through the latent space of a problem to actually help you learn. And let's look at how they've revolutionized something as classic as sentiment analysis. The old models just looked for positive or negative keywords, but modern LLMs, they map entire sentences into a high-dimensional, dense vector space. In this space, sentiment is deeply, deeply contextualized. Because the model understands global context through self-attention, it effortlessly resolves ambiguity, it accurately handles negated polarity across super long sentences, and it can even detect subtle human sarcasm, which, let's be real, is pretty impressive. So the crucial point I want to leave you with is this. We have conquered the quadratic bottlenecks of those early attention mechanisms. We've moved from simple text predictors to agentic workflows that can write code, reason through logic, and seamlessly integrate with the digital world. The architecture is mapped out, the pipelines are highly optimized, and the tools are right there in your hands. So the only question left for your next interview and really for your career is, what are you going to build with this incredible technology?